Hi everyone, welcome back. Last time we talked about how to use Gaussian elimination to solve a system of 3 equations and 3 unknown. So now let's increase the number of variables and see what happens. So consider example 5. Given now we have 3 equations, but we have 5 unknown. So this guy is actually in R5. Okay, so we have 3 equations in R5. So what is the echelon matrix? Solve the system by back substitution. So first, let's write down the augmented coefficient matrix. So the first one, we have 1, x1, minus 2x2, 3, x3, and 2, x4, 1, x5, and the right-hand side is 10. The next one, we have x3, 1x3, and 2x5, and -3. And the next one, we have 1x4, minus 4x5, and 7. So this is the augmented coefficient matrix. Well, actually, you can see this matrix is actually already an echelon matrix, right? So we don't need to do a Gaussian elimination in this case. But in general, given a linear system, we need to use Gaussian elimination to get to the echelon matrix. But this guy is already echelon matrix. Now let's see. The first column corresponds to the coefficients of x1. Second column corresponds to the coefficient of x2. And then third column x3, x4, x5, and this is the right hand side. Now let's look at the leading coefficients. The leading coefficient of the first row is this guy, the 1, 1 entry. And then the leading coefficient of the second row is 1. This is the 3, 1 entry. The leading coefficient of the third row is also 1. This is the 4, 1 entry. Okay, now let's see. The first column, we have a leading entry, right? But do you see the second column? We don't have a leading entry. The third column, we have a leading entry. The fourth column, we have a leading entry. But the fifth column, we don't have leading entries. So those two columns, they have no leading entries. Okay. What does that mean by saying they have no leading entries? So it means x2 and x5, they are free. So they are free, so we can let them be a parameter s and t. So here, actually, we get 2 parameter family. So let's let x2 be s, x5 be t. And then let's do back substitution. The last row tells us that x4 minus 4x5 is 7, right? So what happened? Okay, then x4 is 4x5 plus 7, right? Okay, and then x5 is t, so we have 4t plus 7. How about the second row? Actually, the second row is in the problem. x3 plus 2x5 is -3. So x3 is -2x5 minus 3. x5 is t. And then finally, how about the first row? The first row corresponds to the first equation. And we can solve for x1. So x1, we move all the other terms to the right-hand side. So we have 2x2 minus 3x3 minus 2x4 minus x5 plus 10. Well, x2 is s, but x3 is 2t minus 3. x4 is 4t plus 7. x5 is t. Okay, now let's distribute it. 3 times 2 is 6. 3 times 3, 9. 2 times 4, 8. 2 times 7 minus 14. Okay, how many t are there? Minus 6, minus 8, minus 1. So that's negative 15. And what is the constant? 9 and 10 and 14. So it's like 19 minus 14, which is 5. Alright, let's double check. Oh, do you see I have made a mistake here? This is negative 2t. So negative 2t here. Then it becomes positive 6t. So positive 6t minus 18 is negative 2. And negative 1 minus 3. Okay, so the answer is 2s minus 3t plus 5. Okay, so it's very important to check our work, because sometimes we might make mistakes, and right, we are all human beings, we make mistakes, so it's very important to check our work. Okay, so do you get this answer now? Alright, so let's express it in the coordinates. As x1 is 2s minus 3t plus 5, x2 is s, x3 is minus 2t minus 3, x4 is 4t plus 7, x5 is t. And t and s, they are real numbers. Okay, so this is the answer. We have 2 parameter family, so it means there are infinitely many solutions. So infinitely many solutions. Okay, so this is the answer to example 5. Alright, let's continue. Okay, now if I give you an echelon matrix, you should be able to tell me if there is a unique solution, or no solution, or infinitely many solution. So let's try some with a parameter in the equations to start. So let's look at example 6. Find the value for k so that the linear system has a unique solution, no solution, and infinitely many solution. Okay, so first of all, we want to write down the arithmetic coefficient matrix. So the arithmetic coefficient matrix, this is 1, 1, 1, 1, and 1, minus 1, 1, 1, 2, 0, k, 2. So this is the arithmetic coefficient matrix. So we want to get an echelon form. So first step, we want to make the 1 entry to be 1. If this is 1, then we just use it to kill the entries below it. So how do we kill the entries below it? We use minus row 1 add to row 2. And the first row stay the same. 1 minus 1, 0. Negative 1 minus 1 is negative 2. 1 minus 1, 0. 1 minus 1, 0. Alright, and then next, 2. So how do we get rid of the 2? We use minus 2 row 1, add to row 3. And then we get 2 minus 2 is 0. 0 minus 2 is negative 2. K minus 2. 2 minus 2 is 0. So far, so good, everyone. Okay. Actually, next, do you see this guy is already the same with this guy? So we don't have to make the 2 entry to be 1. We already can use this guy to kill the entry below it. So we can use negative R2 add to R3. Then we get 1, 1, 1, 1. 0 minus 2, 0, 0, 0, 0, k minus 2, 0. Okay, so this is the echelon form, right? And the first column corresponds to the coefficients of x1. Second column corresponds to the coefficients of x2. Third column corresponds to the coefficients of x3. Last column corresponds to the coefficients of our right-hand side. Okay, now once we get the echelon form, we do back substitution. Okay, so back substitution, it means we look at the last row. Last row, here we get k minus 2 times x3 equals 0. Be careful because the common mistake is student will forget to put the x3. The student will put, oh, k minus 2 is 0, so k equals 2, done. No, 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 no. K minus 2 is the coefficient of x3. Okay, so the last row is k minus 2 times x3 equals to 0. And another common mistake is students will forget the parentheses. So don't forget the parentheses. The parentheses is super important. Okay, now look at the last row. When do we have a unit solution? When do we have a no solution? And when do we have infinite many solution? Okay, let's talk about in general. So in general, let's say if we have okay, let's say if we have a x3 equals to b, a and b are some number constants. Okay, when do we have a unit solution? Well, so in order to get a unit solution, we want to be able to solve for x3, right? And then we can plug in the second row to find x2, and we can plug in the first row to find x1. So when do we have a unit solution? We want to be able to solve for x3. So if we solve for x3, we get x3 is b over 8. In order to have this guy make sense, we need the denominator not equal to 0. So that's why here, in order to get a unit solution, you look at the last row and you want the coefficient of x3. It's not 0. Then we can solve for x3, and then we can plug into the second equation and solve for x1 and x2, right? Yeah, when we plug in the first equation, we can solve for x1. Okay, when do we have no solution? Well, that is when a is 0. Okay, remember when do we see no solution? We always see like 0 equals some number which is not 0. Then we get a contradiction. Or this is impossible, right? 0 cannot be a number which is not 0. So how can we get this? Well, we get this if we have a is 0 and b is not 0. So if a is 0, you see 0 times x3 is 0, and b is not 0. So this is what we want. Okay, we can get no solution if the coefficient of x3 is 0, but the right-hand side is not 0. And then when do we get infinitely many solution? So infinitely many solution. Well, if we get 0 equals 0, we get infinite many solutions. 0 equals 0 means the last row is just useless, right? So it's like then we can have two planes intersects. We either have the intersection is a line, or the two planes are the same plane. So we get a two parameter family. Okay, so so the last row 0 equals 0, it means a is 0 and b is 0. Then we can get 0 equals 0. So this is in general, okay, in general. We look at the last row. But for some other problem, maybe you need to look at the second row. For example, if your echelon form is something like 1, 2, 3, 4, 0, k, 1, 2, and then 0, 0, 1, 2, something like this. Sorry, maybe 1, 1, 4, 1, 1. Okay. In this case, the last row tells us that x3 is 1. Then we know. Okay, and then the second row will tell us that k times x2 plus x3 is 1 equals to 2. Well, it means kx2 equals to 1. So that's why you look at the second row in this case. Okay? But in general, you look at the last row and then try to back substitution and solve x1, x3, x2, and x1. Okay? Okay, come back to our problem. Let me change back the orange color. So now, okay, when do we have a unit solution? A unit solution when the coefficient of x3 is not 0. So which means k minus 2 is not 0. So k is not 2. Okay? So k is not 2. So this is what we get unit solution. A unit solution when k is not 2. Okay, when do we get no solution? Well, no solution, we need the left hand side. We want the k minus 2 is 0. And then the right hand side, oh, do you see that the right hand side is 0? We want it to be some number which is not 0, but this is 0, so none. No k can give us no solution. Okay, so none. Okay, no k can give us no solution. So the third one, infinitely many solutions. Well, that is when a, which is k minus 2, is 0, and the right hand side is already 0, so good. So right hand side is 0, which is good. Okay, but the last one we need the right hand side is not 0, which is not good. Okay, but this guy is good, so we get k equals to 2. So when k equals to 2, we have infinitely many solutions. When k does not equal to 2, we have a unique solution. Okay, so now we solve the example 6. We find the values k so that the system has a unique solution, no solution, and infinite many solutions. Alright, so now let's continue. Okay, so keep this in mind. Okay. Example 7. Find the values for k so that the linear system has a unique solution, no solution, and infinitely many solutions. So here we are given the echelon matrix. So we already have the echelon matrix. So remember the first row column corresponds to the coefficient of x1, second column x2, third column x3, and then the last column is the right hand side. Alright, and then let's look at the last row. So last row tells us that k plus 5 times x3 equals to 3. Okay, when do we have a unique solution? We have a unique solution if the coefficient of x3 is not 0. Then we can solve for x3. Actually, we don't care what the right hand side is. It could be 0 or it could be not 0. Does not matter, because it would just affect the value of x3. But in any cases, we still have a unit solution. Okay, so a unit solution when the coefficient of x3 is not 0. So we have k is not -5. Okay, so this is a unit solution. And then how about no solution? Well, no solution is when the coefficient of x3, which is k plus 5, is 0, and the right hand side is not 0. Ooh, good, because the right hand side is 3 is not 0, so we're good. Okay, so and then we just solve for k is -5. So when k equals to -5, the linear system has no solution. And how about infinitely many solutions? Well, that is when the coefficients of x3 is 0, but the right hand side is 0. But in our case, 3, so 3 is not 0, so we fail. Okay, we fail. So no k. So no k can give us infinitely many solutions. Do you have the same answer? Okay. Alright, how about example 5? So, yeah, remember to pause the video and try to work on this problem. Okay? Are you ready to go over together? Okay, so let's see. This guy is already in the echelon form. So, first column corresponds to the coefficients of x1, and x2, x3. This is the right hand side. Okay, look at the last row. Well, last row gives us 0 times x1 plus 0 times x2 plus 0 times x3, so which is 0, equals the right hand side r minus 4. Okay, when do we have a unique solution? Well, no way, because your left hand side you don't ever see, you don't see x1, x2, or x3, so no, none k. No k can give us a unique solution. 2. Remember 2, no solution. No solution, we want to have 0 equals to some number which is not 0. How do we make it not 0? Oh, we just need to make r minus 4 is not 0. Then r is not 4. Okay. And then next, how do we get infinitely many solutions? Well, remember we want to have 0 equal to 0, so we just make minus 4 to be 0, to be 0. So r is 4 in this case. Alright. And you can see in the problem, if we have one parameter r, then we can only have 2 of the cases. Okay, so in this example, we have case 2 and 3. The last example, we have case 1 and 2. And then the previous example, we have the case 1 and 3. So only one parameter. Okay, then we only have 2 cases. So is it possible we have 3 cases? Yes. If we have 2 parameters, for example here, we have k and h, then we can have all 3 possibilities. Okay, now let's see. This system's, let's first write down the augmented coefficient matrix. So 1x minus 2y equals k, 3x plus hy equals 7. How do we make it as a echelon form. Make the 1 entry 1, but it is already 1, which is good. And then use it to kill the entry below it. We use -3 R1 add to R2. 3, so the first row stay the same. Second row, 3 minus 3 is 0. H minus 3 times -2. So it's like H plus 6. And then 7 minus 3 times K. Is that okay, everyone? So this is x1, x2, and this is the right-hand side. The last row tells us that h plus 6 times x2 equals to 7 minus 3k. Okay, when do we have a unique solution? Well, when the coefficient of x2 in this case is not 0, then we can solve for x2, right? So h is not equal to -6. And then when do we have no solution? Well, no solutions, you need like 0 equals some number which is not 0. So that's why you want h plus 6 to be 0. For the right-hand side, we don't want it to be 0. Okay, solve for h. H is -6. Solve for k. Move the 3k to the other side and divide it by 3 on both sides. Then k is not equal to 7 over 3. Alright, and how about infinitely many solutions? Well, when 0 equals 0, right? So we have h plus 6 is 0, and the right-hand side is also 0. Alright, we get h equals -6, and k equals 7 over 3. Okay? Now, we have, okay, then we finished this problem. Okay, so we find the values of h and k so that the system has a unique solution, or no solution, or infinitely many solution. Do you have the same answer? Okay, so in section 3.2 we talk about Gaussian eliminations and echelon form. Alright, if you have questions, feel free to ask me. Have a nice day. Bye.